Good evening. Welcome to Tuesday at reInvent. It is Tuesday, correct?
Yes.
My name is Steve Kendricks. I am the Senior Manager of Product for ECS in Fargate. With me up on stage is Abhishek. He will be walking through some of the key considerations that you all should encounter when thinking about machine learning on ECS. And also with us today is Frank Fan. He will be walking us through a demo of how to use some of what we're about to talk about in the practice. So, show of hands really quickly, of those who are here, how many of you use ECS today or are considering it? That is almost everybody in the room, although the lights are bright, can't quite see, so good, awesome. Really good to hear from you. I'll give you a little bit of a brief overview of what we're going to be talking about today. There are obviously a number of tracks and sessions here talking about how to use Gen AI at AWS from a variety of options. If you are here, as you said, most of you use ECS today, perhaps you're considering specifically when you're using ECS, how can you use the platform that you're already using to get started with working with Gen AI, specifically new and improved experiences to your customers. Or perhaps you're thinking through, okay, I've been considering working with this, I'm just trying to get something lightweight, started up and easy, let's get through and started with ECS to get that workload running, and we can talk you through that. And maybe you're here to build something more advanced, or you've been asked to look at something about how to build a Gen AI platform as quickly, as simply, and as scalably as possible for yourself. So that's what we're going to talk through here today. You're going to see how to, why to choose ECS, architectural considerations that you should think of when going through ECS, and then you'll see a demo of how to put it into practice with a Gen AI inference application running on ECS with stable diffusion. Okay, so without further ado, I'm going to hand it over to Abhishek, who is going to talk a little bit about some of the challenges with MI today.
Thanks, Steve. Hello, everyone. So let's imagine that you're a DevOps engineer or an architect, and your leadership has entrusted you with building a solution that enables your organization to harness the power of AI ML and Gen AI specifically to deliver new and innovative solutions to your end customers. Now, you might think with the rapidly evolving landscape of Gen AI, with a new set of models coming up every other day, a new set of compute capabilities, new types of accelerators that are getting launched, you might have significantly different challenges for building AI ML applications. Well, we think that's only partially true, because even with your traditional set of applications, you have a set of foundational challenges that you would want to incorporate to deliver scalable solutions to your end customers. And let's now talk about some of these challenges, because we don't think that enabling AI ML workloads specifically will be drastically different than the challenges that you might have already solved for your organizations. So from the top, let's look at flexibility. So when using Gen AI, you might want to have flexibility in the choice of your model, the type of customization that you want to run on the model, the type of runtime you want to use, the types of ML toolkits or libraries that you would want to have access to. You would also want the model and your application to be reliable, both in terms of consistency and the correctness of the results that it delivers, while being highly available to meet the end demands of your customers. You would also want to have the right type of performance to ensure that the kind of experiences that you're building for your customers, whether it's an application like a chatbot, which requires rapid interactions with the customer, or it's a queue-based asynchronous kind of a mode, you would want to have control over making performance choices, especially with regards to the compute infrastructure that you choose. You might also want to have flexibility of the desired accelerator that you would want to use for these sets of workloads. And along with that, scalability, because you would want to scale up your application as well as the underlying layer that's serving maybe a foundational model, both of those to support the growth of the growing demand for your application from your end customers, as well as scale it back down when there is not enough demand or when customers log off, for example. And that's closely related to running a cost optimal solution at scale. And then at the same time, you would want to have access to the right set of tools and capabilities that you require to have the right monitoring as well as troubleshooting and debugging for your application. And underpinning all of these challenges really is you would want to build these solutions in a secure and compliant manner to ensure that you're building the right experiences for your end customers. So a mental model that we really recommend you to consider when building these type of applications is to think about the application as two different layers. One being your customer-facing application. So think of it as, for example, a web-based application where your customer is submitting requests. And then think of your model layer, or rather your model endpoint, as something that is decoupled from your customer-facing application. And the key benefit of this kind of mental model is that you get the benefits which are quite similar to the microservice architecture, wherein once you have decoupled the model server as well as your end application, you can decouple the technology choices that different sets of teams are using, and you would have different teams that you can train and can have the right level of skill sets depending on the technologies that they want to use for both layers. Similarly, you can have both the customer-facing application as well as your underlying model layer scale independently. So in the example of a web-based application, you might want to scale that application based on the number of user sessions or the number of requests submitted by the customers. Whereas your model endpoint that would be supporting these customer requests, you might want to scale that based on the rate at which you are processing the customer requests, which could be something like the backlog of tasks submitted to a queue, for example, if you're using an asynchronous solution. And what this decoupling also enables is it enables your teams and your organization to be more agile in terms of your independently deploying and building these applications. And again, like with the end goal that you are able to deliver results for your own end customers with the faster time to market. So before we go into some of the specifics, I wanted to show a sample high-level architecture of this sort of an AI ML-powered application, where here customers are submitting requests through a web application using a load balancer, and the customer-facing application is basically deployed as an Amazon ECS service, which has a set of tasks that are running and that are scaling based on customer requests. And then on the other side is the model endpoint. And here you can clearly see the benefit of decoupling, where the model endpoint doesn't necessarily have to be an ECS application. It could be hosted on any of the technologies or the service of your choice. And a key benefit of architecting in this manner is, since most of you here today are using ECS already, you probably are, or you are building a set of traditional applications using a similar architecture with ECS, and you can just infuse and extend that architecture to now use a model which could be deployed using ECS or without ECS, and we'll shortly see some of the options that you have at hand. So now let's look at both of the layers. So in terms of hosting your customer-facing application, we would highly recommend you to consider a serverless technology, because it really enables development teams and you to move faster from idea to completion and to deliver results faster to your customers, because you do not have to reason about the underlying infrastructure choices, about patching the underlying servers, ensuring that they are meeting the security and compliance requirements, so on and so forth. A serverless pattern enables, or we really think of serverless in terms of an operational mode, because it enables you to offload all of these undifferentiated tasks to AWS so that you can focus on your core business logic and deliver better results to your customers. Now, in terms of the options that you have for serverless compute, in this chart, we've highlighted the landscape of serverless compute. The two axes that you see here are representing how opinionated one solution is versus the other and the kind of control that you have. And you'll see on the top right where we have AWS Lambda, which is a highly opinionated serverless solution wherein you have to use the Lambda programming model. There are a set of constraints that you have to work with around the execution time, the storage limits, and so on. But it enables you to very quickly get started, especially when you're thinking of building event-driven serverless applications. Now, I want to take a moment talking about why ECS or how ECS belongs in this spectrum. And ECS essentially is a fully managed container orchestration service. And ECS itself, you can think of ECS as a serverless control plane, because with ECS, you don't have to reason about any cluster version updates, installing new type of firmwares, or like ECS takes care of all of this under the hood, and you get all of the new capabilities that ECS is building for you for free without reasoning about any sort of upgrades. And within this serverless control plane on ECS, you have the options in terms of using a serverless data plane, which is AWS Fargate, which again takes it a step further, wherein you have a fully serverless experience, and you get all of the benefits of a serverless architecture. Whereas if you want to have more control over the underlying infrastructure, which may be true especially for AI, ML, or Gen AI applications, because your applications may be more catered to or maybe better served by a specific accelerator that you have used for performance benchmarking, you can get access to those type of compute capabilities when you run Amazon ECS with EC2 compute. So, having looked at the options for your customer-facing application, now let's take a high-level view at some of the options for your hosting your model layer or the model endpoint itself. And again, here it's a spectrum of options, and you can think of the spectrum from the ease of use and the control and configurability that you have. On the extreme end of ease of use is Amazon Bedrock, which is a fully managed serverless API as a service experience, which enables you to get started really quickly, get access to a wide range of foundational models, do fine tuning, and so on. In the middle, there is Amazon SageMaker, which provides you it's a purpose-built service, which provides you an environment to run, build, deploy, and train your ML models. And then on the extreme end of more control and customization is that you can actually self-host your models using Amazon ECS, which is basically a generic container-based solution wherein the Gen AI application itself is just an extension of your existing applications. And again, the choices here are completely up to you depending on the kind of use cases that you have. So let's look at why you may want to think about using your or hosting your model on Amazon ECS compared to the other options that you have. So if your organization already has some level of expertise in running and deploying a model and also running and deploying your services on Amazon ECS, by also deploying your model on ECS, you get the benefits of having consistent tooling so that you're able to extend your existing platform seamlessly to also Gen AI applications. And along with that, you get full control and configurability as well as flexibility of some of the challenges that we discussed about the choice of model that you have, the choice of infrastructure, the choice of libraries that you want to install, so on and so forth. And you get access to the fully managed feature set that ECS has, and it's deep integrations with other AWS services, which enables you to meet your needs around observability, security, application auto-scaling, and when combined with Fargate, you get serverless compute out of the box. And we'll evaluate some of these as we go further today. So let's start with compute options. Now, ECS enables you access to all of the compute options available on AWS. So we already talked about the serverless mode with AWS Fargate and its benefits. And here, specifically for GenAI workloads, we would also recommend you to consider using CPU-based serving, because not all models all the time require an accelerator. Some of the smaller models could potentially be served using CPUs, but of course it depends on your requirements around performance, your latency expectations, and so on. And then in the middle, you have ECS running on EC2 instances, and ECS has a deep integration with auto-scaling groups to seamlessly scale your application, or seamlessly scale your compute infrastructure based on the demands of your application. And it provides you access to all of the available accelerated compute options that are available on AWS today, including the latest and greatest instances that are available with day one support on ECS. And then on the extreme end of the spectrum is Amazon ECS Anywhere, which can enable you to run your AI ML-based workloads on the edge in a hybrid manner. And we see patterns of customers with strict data residency or privacy requirements where they are running their applications in a hybrid mode by collecting the data to run inference on premises while running their models in the cloud. In terms of cost optimization, you also get access to the purchase options and the discount options that exist on EC2, specifically spot instances as well as savings plans, which you get both with Fargate and EC2 compute options. Also, you get access to Graviton-based instances, which provide better price performance, both on Fargate and EC2 compute options with ECS. So in terms of the scalability needs of both your customer-facing application as well as for your model layer, ECS's service auto-scaling capability, which is enabled by ECS's deep integration with AWS application auto-scaling. You get access to a wide range of scaling policies, which you can use with the desired metrics of your choice. So ECS provides you a bunch of predefined metrics like CPU utilization, request count for your load balancers. Also, ECS enables you to use custom metrics, so things like queue depth, backlog in your queue, so on and so forth, which you can use with these scaling policies. Now, in terms of the options that you have here, it's an entire spectrum from more configurability, again, which you get with step scaling, where you can actually define exactly how the scaling policy will behave in terms of the granular step sizes that it will take to increase or decrease your task counts. Then there is target tracking, which is a fully automated mode wherein all you need to think about is the target that you want your application or rather your application or your ECS service to meet. So an example would be that on an average you want your CPU utilization across all of the tasks deployed on your application to be 75%. You can just set that target with the target tracking policy, and then ECS and auto scaling takes care of scaling up and scaling down your application based on load patterns. You can also get schedule scaling or have access to schedule scaling, where you can manually define steps to scale out or scale back down your application. So an example could be that you know that there is a surge happening every morning at 9 a.m. and then the traffic winding down at 5 p.m. every day. So you can define a schedule scaling action by configuring these exact scaling steps. And then predictive scaling, this is the newest scaling policy that we are really excited to launch. This was launched about 2 weeks back. And this is a more proactive and a machine learning based algorithm that we have built, which will automatically look at your historical demand patterns, and when it detects a recurring or a cyclical pattern, so the similar example as 9 a.m. every morning, winding down 5 p.m., or every Monday you get traffic from your customers logging into your applications. Predictive auto-scaling can predict these demand patterns and proactively scale your applications ahead of time. And the key benefit is that you do not have to over-provision your application or do manual workarounds such as using schedule scaling to scale out your application for these demand patterns. A key recommendation that we would like to give you here is to use a combination of target tracking along with predictive scaling. And predictive scaling is something that we built as a complementary policy to your target tracking or to any other scaling policy that you have, because it will provide a safety net to pre-scale your application, while it does not by itself scale down your application. So by using predictive and target tracking together, you can scale your application both on predictive and historical or cyclical patterns, as well as real-time traffic surges that you might have. So having looked at the scaling or the scalability of your services, let's quickly look at the compute infrastructure, which is the underlying layer. Now, a key benefit again here with serverless is that you don't have to think about underlying compute infrastructure, but for your GenAI applications, if you want to run it on a specific accelerator, you might want to use, or you would be using EC2 instances. And in order to scale your underlying infrastructure and your EC2 instances in consonance with your scaling need of your applications, ECS has a solution called Capacity Provider, which automatically scales out or scales down the number of instances that are running. So in this example, you can see that there are requests coming in for 3 tasks, which have been scaled for your service. And then depending on how many instances are required, ECS capacity providers will determine how many instances to launch or to scale out or to scale in. And capacity providers also enable you to use spot capacity and on-demand capacity. So you can have a mix, for example, or use spot capacity when you know that your workloads are more resilient to interruptions. Also, we would recommend you to use auto-scaling group warm pools, specifically for GenAI based applications. So ASG warm pools really shorten the pre-initialize your instances to reduce the time it takes to launch EC2 instances, which might be required given the cost of specifically for larger GPU-based instances. So in terms of storage options, again, you have multiple options here with ECS. You can potentially choose to bundle your model along with your application's container image. And this is something that might work well for traditional applications, but we would caution you against taking this approach for AI ML based applications, because the model size itself could be from several GBs to hundreds of GBs, and bundling that with container images or your application's images can slow down your application load time. You can also use S3 to host your model and then pull it at runtime into your ECS applications or into your containers. And then you can also have access to Elastic File System, which is a fully managed Elastic File System. And shortly we will see a demo of an application where which we have built by using EFS, and which is the recommended option that we will discuss shortly. So finally, to monitor your application, ECS again provides you native integration with Amazon CloudWatch, and especially CloudWatch Container Insights provides you a bunch of different metrics that enable you to monitor and troubleshoot your applications. And we actually launched enhanced CloudWatch Container Insights just earlier this week, which provides you more granular insights or metrics at your task and container level. One quick call out, because we are talking about GenAI and ML applications, is today ECS has a metric for GPU reservation, but it doesn't have GPU utilization or GPU temperature, some of these metrics available out of the box. So you can use a package like NVIDIA Data Center GPU Manager, which you can install on ECS, which we'll shortly see in the demo. And these metrics are being, we have more granular and more specific metrics on the roadmap as well, which as we launch those, you will get them for free with ECS. So then ECS also has a native integration with Firelens, which can enable you to route your logs or your metrics to a partner solution if, for example, you don't want to use CloudWatch or to a different AWS service. And also, AWS X-Ray is a daemon that you can install along with your ECS applications. And this is something that we would recommend if you want to trace end-to-end user requests, especially for AI ML workloads, to really troubleshoot and debug if something is going wrong. So with that, I'll hand over to Steve to describe some of the success stories that we are seeing with our customers on ECS.
Yep. Thank you. Or you can go ahead, man.
Thank you.
Thank you, Abhishek, for that pretty thorough understanding of how exactly you should reason about some of the constraints and some of the ways that you should work through those constraints using Amazon ECS. Customers are already succeeding today with ECS using GenAI today. Here's a few of the customers who are seeing success. Wombo and Scenario both have built GenAI inference workloads, specifically citing the faster time to market that they receive using Fargate and ECS, or in some cases EC2, in some cases Fargate. Kepler used Amazon ECS Anywhere for a hybrid and cloud-based workload to accelerate their ability to bring their machine learning applications to the cloud. And Amazon recently, as you know, Andy talked yesterday about Rufus, right, the new machine learning tool that is helping customers build and shop easier and more personalized touch on the world's largest e-commerce platform. Amazon built Rufus using Trainium and AWS Inferentia EC2 instances through ECS. So customers are seeing success today. We are going to show you how, through a demo here, how customers can be successful through ECS at scale and the simplicity it offers. So thank you, Frank.
Thank you.
Hello, everyone. I'm here with an exciting opportunity for each of you. Imagine you are engaged by a forward-thinking digital company. They want to transform their digital landscape. They engage you to design a real-time inference application to do image generation. What are most important things for you to think of? Here are 3 things you need to focus on. The first one is about reliability. Because you have this front end and back end to the inference, you need to ensure the whole environment is up running all the time, regardless of any planned or unplanned outages. Second one is about performance. The end user doesn't want to wait a very long time to get an image, right? Need to be very careful about latency and throughput. Last but not least, scalability. The end user traffic have lots of uncertainty. How are you going to deal with the spiky workload? And how are you going to scale in during a quiet time to save the cost? So are you ready to take this journey with me? How are we going to deal with this challenge? Awesome. Reliability. Let's look at a conceptual architecture here. Looks as simple. End user send a request to the front end, and front end need to interact with this runtime we call inference endpoint, and load model files generate image, and send the output. Output will be make available to user to view. Simple, right? Which component is most important for reliability? All of them, and also the connectivity between them. So we need to think about the holistic view, how we're going to architect. Let's start with this synchronous mode. Simple. You have an user talk to my inference endpoint. You can fail fast, it's simple. But some consideration here is, what if you have spiky workload here and your backend cannot keep up? You may have performance throttling issues. Another challenge is, what if you have inference endpoint have outage, right? The end user will see the error message straight away. Any ideas? Can we do a better job? Yeah, we can make a asynchronous way. So this is what we are today. How about we have a broker in the middle? You can say we decouple this. And user send a request, broker acknowledges that, I got it. And then broker will send, or the backend will pull the request, and I got it. Benefit for that is you improve the scalability and flexibility. And most importantly, it's more reliable. So this is a one-node implementation. You have a front end, you have user send lots of messages, right? 4 messages. And event router here will, based on your attribute, to send to different queues. Why is that? Because both of them running, right? It improves the reliability. If one goes down, another one is working. And also they are running in parallel. It's more efficient. But last one, you can say right-hand side. I have that inference endpoint, right? Inference endpoint and can associate it with different instance type. Because for the premium user, you want to give them fastest, the best instance type. But for the free users, maybe you use cost-effective ones. You can also associate a different runtime. Because today, open source community have lots of runtime for interact with stable diffusion for different use cases, right? You may have one use just foundation model. Another one, you can combine it with other extension model to generate very specific style. I will show you later on. Now let's think about how we're going to implement this solution using AWS technologies. From left-hand side, end user, you leverage API gateway. And you use API key for authentication, authorization. And Lambda function want to validate because you cannot get any method to get in. When Lambda validate that, it will pass on to SNS, simple notification service. And from there, simple notification service based on attribute will pass on to different queues. And here, we can use different runtime. When I say runtime, it's more about inference endpoint. Can use different open source technologies. Either you can do a simple, just a generation of image, or you can use config UI, which is very advanced. You can have workflows, how you can generate different steps about the image. Let's talk about the inference endpoint. We zoom in that component. Left-hand side, I already have message in my SQS. And right-hand side, there are 2 key components here. Another one I mentioned about SD runtime, that's inference endpoint. But today, lots of open source runtime doesn't support queue natively. We need to do something about it. So we wrote an agent. What agent does is it do a transformation for the message to make it can be recognized by that runtime, but also acting as a middleman to make sure these 2 can work together. All right, we talk about front end, we talk about back end. How about we put everything together? Let's see how the workflow look like. All right, let's start with number 1, task. Step 1, basically I have job in the queue, and then the agent will pull the message in the agent and then pass on to the SD runtime, load model files to generate image. probably you have a question. What if you have a failure? Because we talk about reliability, right? What if your inference endpoint just fails? So that message in that SQS queue won't be deleted at this stage. It's just hidden, right? If it's failed, another new task will come up and retry that message. Step 2, you finish the image generation and save to the S3 bucket. And step 3, you want to notify your end user, I complete the task, here's the image for you to view. And then step 4, everything completed successfully, I can delete the message. As you can see, this architecture maximizes reliability, and regardless any planned or unplanned failure of your backend. All right, we need to move on to next challenge, performance. Can you think where we should start with about performance? How you minimize latency of end users? You have some thought in your mind? Love it. Turn the model fast. All right, you're right. There are two key components. Inference endpoint. Can we bring the inference endpoint quickly? And most importantly, can we load the model files fast so they can two work together? Let's zoom in these two components and see what it can do. Probably we need to think about what chip we need to host, right? This inference endpoint. What instance type? We have a broad range of these chips for you to choose from. CPU, very cost-effective, and it's general purpose. You don't need to do much customization. It's very good with serial execution. If you use a small model and your latency is not that rigid, CPU may be most cost-effective way. It does work. In some cases, GPU works better because the model is large, need very low latency. GPU really good with parallel execution. Right? That's why inference endpoint really need that. If you look at another end of the spectrum, this A6, application-specific integrated circuits, such as AWS Inferentia, just designed for inference workload. Because it's purpose-built, highly performant, very cost-effective. Some consideration for you to think if you want to adopt these technologies, ensure the model is support that because it rely on AWS Neuron SDK to expose a certain operations. So need to make sure your model can be supported. So which one we need to choose? It's not either or. Depend on use cases, right? You can have a combination of these different instance type for your use cases. So based on your flexibility and also how much you want to specialize and from cost perspective. Imagine you are going to choose GPU. So GPU, you come up with GPU type and also instance family, right? So here in the middle, you can see A10, that's a NVIDIA GPU card family. And G5, that instance type, come up with that particular hardware. Well, how are you going to determine the performance? Which one you to choose from? There are so many. So some key factors I invited you to consider is the GPU family, and also the GPU memory size and bandwidth. So in this case, the G6E stands out because on the right-hand side, you can see the specifications. It can have up to 8 GPUs, and each of them can have at least 48 gig GPU memory. And lots of the instance is single card, which is perfect for the real-time inference workload. Left-hand side, you see the graph. Compare with previous generations like G5 or G6, they have at least 3 times better performance. Now we come to a question, how can maximize the performance? How can make my endpoint ready to receive jobs? 3 main steps. The first one, how quickly can I load my backend instance and put that in the ECS? Second one, how quickly can I load the container image? They are big. Thirdly, where I'm going to put my model files, how can I load them quickly? Let's address them one by one. The host, you can choose, how about I over-provisioning that, right? Sitting there idle, waiting for my job. Cool. Instead, we choose to use warm pools. Warm pools is pre-initialized instance there, ready. Instead of load the instance in a cold way, it's ready for you to load. It saves you cost because you don't have to over-provision that. And second thing is about container image. They are quite big. So some container image, like our inference endpoint, they need to leverage lots of the PyTorch dependencies, CUDA drivers. It could be up to 14 gig. It takes 6 minutes to load them. Can we do a better job? And there's a big question mark about model. We'll cover that in a second. For the container image, can you think of any way we can fast track the load of container image? Any thought in your mind? So basically, container image, thank you. One option is bake that in the host. But the challenge for that is every time you make change of container image, you need to run an update of your EC2 fleet. It's not a trivial task if you have a large environment. Now we explore the new way, very innovative way. This graph, let's draw your attention to the left-hand side. There's a thing called BottleRocket. It's a purpose-built Linux OS designed by AWS. And this BottleRocket OS have 2 volumes. One is OS volume, OS and security patches. They have its own life cycle to update that. Another volume is data volume. In this case, how about we load this inference endpoint image, because it's quite big, right, to this data volume. Now, cool, we have data volume. On the right-hand side, this up-running environment of EC2 instances already in the ECS. How about we just do a snapshot of this EBS volume and map to my existing ECS instance, also using BottleRocket, right? You just simply attach it and then load these files to memory. So as you can see, this process is important to the fast mapping. So the performance of EBS is crucial. So we max it out to 1,000 megabyte. As soon as it loads to the memory, well, cool. We don't need that performance. We can schedule Lambda function to reduce the capacity. All right. So in terms of performance, another one is load the files. So model files, we can put that in Amazon EFX, which is provide better latency, throughput, and also in an elastic way. So by doing that, you can significantly reduce the time to load the files. You can also choose to offload some container image files to the EFS. In this case, as you can see, we reduce the image size from 20 gig to less than 1 gig and can load it up in less than 1 minute. And model loading time can be reduced from 30 seconds to 10 seconds. Performance is also related to monitoring because we need to understand how our resources is utilized and how environment does it meet our latency requirement. So we have 2 patterns here. The first pattern we call use sidecar pattern and using ADOT, which is Amazon distro of telemetry, which using open telemetry project to run it as a container to get metrics, trace logs, and traces from another container running inside the tasks and push to the backend. Another more popular pattern is centralized pattern. Here, we just use that A dot running in a dedicated task, can capture information from other tasks and push information to backend. Now, we need to move on to GPU. So we leverage the DCGM, which is NVIDIA tooling, to expose lots of GPU metrics here for you to monitor the utilization. We still have a challenge, right? Scalability, thanks for mentioning that. How quickly we can scale out? We need to focus on the inference endpoint. From here, you basically leverage metrics, pass on to auto-scaling, application auto-scaling, you have policy there, and your ECS will stop or start tasks. What metrics we are going to use? Because we use this asynchronous architecture, we already have jobs or messages in the queue. We simply just use all the pending messages in that queue, right? Simple. So let's demonstrate how it works. You have this working, just one task, it's fine, but I have more jobs coming in, right? I need to have more tasks pending. Why is pending? I need backend instance to fulfill that need, right? Because we have one pool, we can pre-initialize some instance already. And here, we can also use spot instance. Because it's so reliable, even when spot is not available, you wouldn't lose that message. Then you can see the gray area, these two pending tasks, is active. Do you see some issues about the architecture? However, it doesn't consider how long these jobs be processed, right? For example, if you look at the diagram here on the right, let's imagine you have already 3 tasks actively running, and you have 12 pending jobs in the queue. So 12 divided by 3, that's 4 pending jobs per task, easy. But during load testing, we found when it's reached 10, it's struggling. You get a performance degradation. So we use the 10, which is a custom metrics. Basically use your queue depths, pending jobs, divided by your active tasks, and use calculate that with a custom metrics we call backlog per task as a metrics to do the scaling, which is more accurate. Having said that, let's have a demo. How we're going to demonstrate all these technologies we already mentioned. So this environment, you can see 2 services here. You have a dot that expose that metrics or GPU. And this next service, Q service, the inference endpoint service. If you look at task configuration here, there are 4 main containers of these tasks. Inference API do the inference, and Q agent we mentioned need to get a message from the queue and save the image back to S3 bucket. X-ray will capture the tracing information. DCGM, it will expose GPU metrics. Because this GPU resources need to be shared by both of them, we need to enable the support for GPU in the launch template. And we changed default runtime from Docker to NVIDIA. So the containers can share these GPU resources inside that task. How to fast load the model files? We create an EFS volume here. We simply just load files in the volume. And from container perspective, you just create a mount point to access that files already there. Super simple. If you have new models, you dump it into the volume. Automatically, it's available for the container to consume. Let's simulate testing. So this is the interface for X-ray. And then I already have a simple JSON file to define the prompt, just one line, a horse running. And I have a script to generate a message. That message will be pass on to API gateway, and so on and so forth for inference endpoint to process. And when we refresh, you can see, because we already have X-ray deployed, this trace has been captured. From left-hand side, pass on to API gateway, Lambda function validated a message, and then SNS got that message based on attribute, pass on to the SQS queue. Queue agent pull the job, process that with inference endpoint, and save it to the S3 bucket. In this duration, you can see how long it takes, right? It's roughly 1.4 seconds to generate the image. Very powerful. Let's go through our output. This S3 bucket, the image already there. When you look at the image, it does work. Simple, right? But perhaps you have some unique style. You want to make it more different use cases. Here, we choose a different model. Still a simple prompt, but I use LoRa, which is another extension model, can work together with foundation model, Stable Diffusion. I didn't change anything else, because it's a model already pre-trained with a specific style of the picture. Let's see what outcome look like. I need to change and rename the file name, so make sure this is taken into effect. Then we just run the script. It's the same thing, send to the API gateway and do the process. And we just need to go to the S3 bucket. It should have a new image. Here we go. And open up. We make sure the right one, the latest one, is the one we just generated. It's a very different style, right? It's Chinese painting style, because it already uses different model. You can do lots of these things using different models, give you a different style and to meet your use cases. We just talk about single image generation. How about a production environment? You have so many requests coming in. We need to ensure it can scale out quickly and scale in. So here, I run load testing, continuously sending requests. But let's see how we're going to react. So here, we go to the dashboard. Remember we mentioned about the metrics we used for scaling? Backlog per task, right? Here, it's still no backlog, right? Scaling not happening yet, but give some time. This is our custom metrics, right? Based on the pending jobs divided by active tasks to measure how busy my environment is at the moment and make decision. And here we go. In an event, we can see lots of tasks has been triggered, but it's in a pending state. Task is pending because we're still waiting for backend EC2 instance to be ready. It will talk with application autoscaler to do that, right? Here we go. We already see that this metrics going up to 500 or 600, so because they triggered more tasks. And then we need to look at the desired account. That's our want to scale to 10 tasks. And take some time. I just forward this video recording. You can see the capacity provider received the signal to scale backend EC2 instance to be ready. And once it's ready, you can see the growth of the tasks and CPU utilization stabilized. So this basically shows you how scaling works. And if you go back to the EC2 console, all of them is up running, so working as expected. When we complete this testing, it will shrink. So save your cost. That's end of demo. But just do a quick recap about what we covered in this session. Can I ask you to draw the attention to the top one, flexibility? Why is it important? This stable diffusion ecosystem is so big. And image generation, you can leverage different type of the foundation models like stable diffusion, flux, or even new models coming up. How can we quickly switch them, compare the difference, and choose the right one? Beyond that, like I showed you earlier, different use cases, you may need to leverage extension models, like LoRa, give you a specific style, like some control net, can change the pose of the image, so on and so forth. So important for you to have flexibility to deal with different use cases. Reliability, that's very important, right? So from end to end, you want to make sure environment always up running. And we leverage Amazon ECS, along with other serverless technologies like API Gateway, Lambda, SNS, SQS. They all have inherent scalability and reliability of the environment. So provide the whole application stack, make it reliable. Performance. How can we leverage the latest, the fastest instance type, like GPU instances or AWS inferentia or GCPU for your different use cases? You have the flexibility for ECS to use all of them. Together with AWS storage services like Amazon EFS, you can load model files quickly to fast load your model files. Scalability, because we already have inherent scalability inside ECS using meaningful metrics, talking with application autoscaler, and use capacity provider to scale your backend environment quickly. You can also pre-warm them using warm pools. Observability is very important because it not only just show you it's working as expected, but you can monitor GPU utilization, allocation, and fine-tune the whole environment. Cost, very important, right? When you're running a scale-out environment, we can scale out and scale in, save your cost. And don't forget about the spot instance. Because a reliable environment, even the spot instance sometimes is not available, you wouldn't get lost that message. And it would be retried and continue on. It just takes a slightly longer time. So here we go. We have all the benefits here. And I would encourage you to pay attention to some sessions here. If you want to know more, they are really relevant to this topic. And please take your phone out to scan this code. We already have all the slides. We have all the steps and blog articles already published, right? You can download them straight away. So all the details for you to learn how we can optimize the environment for AI ML workload. But in the end, I would like to thank you to be with me and thank to my co-presenters. I want to ask you a big favor. Can you please do a survey? It's super important for us to learn your feedback so we can create a better solution and also benefit more people. If you can do that, it will be much appreciated. Thank you all, and enjoy your rest of the day.